In this video, we're going to cover section 8.2 on hydrohalogenation. Now, when we react an alkene with a hydrogen halide, so shown here is HX, where X can be a chlorine, bromine, or iodine atom, this results in the addition reaction called hydrohalogenation. So as you can see in this example, we have our symmetrical alkene, adding to it hydrobromic acid, so HBr, and at low temperature what we observe is the addition product. So you can see that we have a new carbon-bromine bond formed and a new carbon-hydrogen bond, which is not shown in our bond line structure. And so in this example, because it is a symmetrical alkene, we only observe a single product. Now, if the alkene is unsymmetrical, that is, the R groups attached to the carbon-carbon double bond are not identical and not the same, then we will have different regioisomers. So we'll look at how we can predict where that new carbon-bromine bond is going to form. Now in this example, we have what we refer to as an unsymmetrical alkene. One of the carbons of the double bond has a methyl group and the other has two methyl groups. And so the question becomes, where does this halogen X, where does it add? Will it add and form a new covalent bond between this carbon or this carbon? And how we can predict the placement of that particular atom has to do with the mechanistic details. And so if we look at the mechanism, we can understand why we see the product distribution that we see. So when the halogen is placed at the more highly substituted position of the original alkene, we refer to this regiochemical preference as Markovnikov addition. It's a commonly used term, and so we still use it today to describe that particular placement, that the halogen will end up on the carbon that's more highly substituted when you look at the substitution of the original alkene. And we refer to the opposite if the halogen ends up at the least substituted carbon of that original alkene. We refer to that as anti-Markovnikov addition. So this reaction is regioselective. We can obtain regioisomers. And so we'll look at the details of this reaction to understand why we get these particular placements. So as I just mentioned, if the halogen is placed at the less substituted position, this regiochemical preference is called anti-Markovnikov addition. And in this example, we have a disubstituted alkene. One carbon of the double bond has two methyl groups. The other carbon of the double bond has two hydrogens attached to it. And you see here that when we add HBr in the presence of another reagent, which we'll discuss in a moment, we end up with a new carbon-bromine bond at the least substituted position of that original alkene. So you can see from this diagram here that the regiochemical outcome of a hydrohalogenation reaction, it really depends on the reagents that we're using. So in both cases, we're adding HX, or in this case, hydrogen bromide, but to obtain the anti-Markovnikov addition product, we must add another reagent to the mix. And as shown, this is abbreviation for an alkyl peroxide. And so we'll see that how this addition of alkyl peroxide changes the reaction mechanism. And because the mechanistic details are different in these two reactions, the outcomes, the products of those reactions will also be different. So if we wish to form the Markovnikov addition product, we would add HX in the absence of any peroxide. But if we wish to form the anti-Markovnikov addition product as our major product, then we would add the same hydrohalogen, but in the presence of this alkyl peroxide. So now let's look at the mechanism for hydrohalogenation, specifically Markovnikov addition. So in the presence of a hydrogen halide and an unsymmetrical alkene, The first step that we see in this mechanism, this general mechanism, is the proton transfer. So again, the alkene is acting like a weak base. It's reacting with a strong acid. And so we see we have a proton transfer. We draw a curved arrow from the pi bond, and it's going to remove that hydrogen as a proton. So it's a proton transfer. Now notice the intermediate that's formed. We form in this particular instance a tertiary carbocation. And this is typical of Markovnikov addition, that the first step will involve a proton transfer in which the more stable carbocation will be formed. Now you could imagine that there could have been the possibility for this particular carbocation, but the secondary carbocation being less stable than the tertiary, we don't see this forming experimentally. So we form a tertiary carbocation as an intermediate, and the second step is nucleophilic attack by the bromide. So the bromide is going to form a new bromine carbon bond to give you your final alkyl halide. And we can look at that mechanism using an energy diagram. We have two steps, so that implies there's that single intermediate shown here as this minima, but we have our first barrier is our proton transfer, and the second barrier is our nucleophilic attack. And so going from our alkene through this addition process, we end up with a more stable product, that of the alkyl halide. Now, again, key to this mechanism and the Markovnikov addition is that in that first step, we form a tertiary carbocation, but not the secondary carbocation. So we're going to see our products being derived from this particular carbocation, the more stable of the two. And again, recall that that stability is a result of what we refer to as hyperconjugation. The greater the number of substituents around a particular carbocation center, the more stable it will be. And we can take a closer look at the energy diagram for this particular hydrohalogenation reaction, in which the transition state, you can see the transition state leading to the secondary carbocation would place a partial positive charge. And so this is going to be less stable than this particular transition state, where the partial positive charge is at a tertiary center. And so this gives rise to a lower energy, and therefore this will be the most likely path in which this reaction will proceed by, giving you the tertiary carbocation as the intermediate and not the higher energy secondary carbocation. So again, the stability of the intermediate is key for the regioselectivity of this reaction. So now let's look at some of the stereochemical aspects of this particular reaction. If hydrohalogenation results in the formation of a chiral center, we're going to find that the observed product ratio will be a mixture of the different enantiomers for that particular addition reaction. So in this particular example, we have a unsymmetrical alkene, we have hydrogen chloride as our reactant, and we would expect to form this particular 2-chlorobutane as our product. Note that this particular carbon has 4 different substituents attached to it, so therefore this is a chirality center. In this reaction, there are actually 2 Markovnikov products that are formed in a 50-50 ratio. And so we call this mixture of enantiomers a racemic mixture. And you can see that the net result of this reaction is that we'll form 50% R and 50% S. And that's because when we generate that carbocation, there can be nucleophilic attack from either side. We can have nucleophilic attack from, let's say, the top side of the plane associated with that sp2 hybridized carbocation center, or we could have attack from underside that plane. And so due to the equal probability that the halide will attack the carbocation from either side, so we end up with a mixture of enantiomers as a result. Now, when carbocation rearrangements can occur, they do occur. So similar to what we've seen previously, if we generate in that first step, in that first proton transfer step, as in this example, if we were to generate a secondary carbocation, this system will undergo rearrangement to form the tertiary carbocation. So you can see there's a hydride shift. that hydride shift will result in the tertiary carbocation, which will undergo attack by the halide. Now, we will still have a product distribution or a mixture of products as a result of this reaction, again, due to the fact that some of this secondary will react with the chloride as well as the tertiary. So you can see that 60% of the product, the major product of this reaction, will be the rearranged product, that is the alkyl halide resulting from chloride attacking the tertiary carbocation, but yet we'll still have a large percentage due to the chloride attacking the less stable carbocation. So in this particular reaction, we will end up with a mixture, but the major product will be from the rearranged carbocation. So now let's look at the mechanism for the anti-Markovnikov addition of HBr to an unsymmetrical alkene to see why the regioselectivity is different in the presence of an alkyl peroxide. The alkyl peroxide shown here includes a single bond between two oxygen atoms, and these are some of the more weaker bonds found in organic chem. And so in the presence of a little bit of heat, what we observe is homolytic cleavage of the alkyl peroxide to give us an alkoxy radical. What we mean by this is that when we break this bond, a single electron ends up on each of the oxygen centers, generating a radical species. This is only one of two radical reactions that we'll look at. Most of the reactions that we will look at involve the movement of two electrons at one time. But this is an example where we generate a radical species that contains a single electron on an atomic center and how it can interact with other reagents in our mixture. And so we see that this alkoxy radical is really the reactive species that reacts with HBr. And in this reaction, we refer to this not as a proton transfer, but a hydrogen abstraction, because we're taking the hydrogen atom with its single electron in the formation of a new bond with this oxygen atom. And notice that the curved arrows that we're using are these single barbed arrowheads as opposed to the double barbed arrowheads that we've used previously. And so the movement of a single electron, one from the oxygen center, one electron from this HBr bond, that generates a molecule of alcohol. But the reactive species that we're generating in this initiation step is really the bromine radical. And so this becomes the reactive species that interacts with our unsymmetrical alkene. So once we form that bromine radical, it then will react with the alkene. And so what we'll see is a sharing of that single electron with a single electron of the pi system in our alkene. And this is our propagation step. And so we form a new bromine carbon bond with this carbon, leaving us with a radical at the other carbon. And I'll point out that what we're forming here is a tertiary radical. And so we'll see on the next slide that tertiary radicals are more stable than secondary radicals. And this is the main reason giving rise to the regioselectivity of this reaction compared to hydrohalogenation in the absence of the alkoxy radicals. So as a final step, we have a second hydrogen abstraction reaction from another molecule of HBr, and that's going to give us the neutral alkyl halide. We also generate in this final step another bromine radical. This bromine radical is free then to react with additional molecules of the alkene in a similar manner to generate more of the alkyl bromide. But at some point when the alkene runs out and we have no more alkene to react with our radical systems, the final termination step will occur between two bromine radicals to generate a molecule of diatomic Br2. So this is, again, the reason why we see a difference in the regioselectivity. We don't go through a carbocation intermediate, we're going through a radical intermediate. And again, just to clarify as to the regioselectivity and the preference for the observed product, has to do with the fact that we are forming a more stable tertiary radical by forming a new carbon-bromine bond with the least highly substituted carbon, because that will generate a tertiary radical as opposed to the opposite, or I guess the other option, which would be a secondary radical. And there's no experimental evidence for this forming. So the preferred radical intermediate, the tertiary radical, is formed in that first step. And so again, just to parallel what we've seen previously, the ionic mechanism involved the formation of a tertiary carbocation, whereas the radical mechanism that we just discussed involves the formation of a tertiary radical. And so the more stable the intermediate, that will most likely be the pathway in which the reaction will proceed by. So if you have any questions about hydrohalogenation, by all means reach out to me, send me an email, and we can set up a Zoom appointment to discuss it in further detail. Thank you.